So an industrial method for the production of elemental zinc from its ore is to roast the crude oil in oxygen and then react it with carbon monoxide. The following reactions describe the chemical process. So what you see is it's a two-step process. A 10 kilogram sample of an ore containing zinc sulfide was chemically treated according to the reactions described above, producing 2.85 kilograms of zinc. Determine the percentage of zinc sulfide contained in the original sample of the ore. So what happens is you have like this ore of, and in it, embedded in it, is you have some zinc sulfide. So this 10 kilograms, and then you have this zinc sulfide, and they were able to get 2.85 kilograms of zinc. So it wants to determine the percentage of zinc sulfide contained in the original sample of the ore. So the first thing we're going to do is we're going to start out with how much zinc did we end up with. And we ended up with 2.85 kilograms of zinc. First thing I'm going to do right off the bat is I'm going to take 2.85 kilograms and I'm going to convert that to grams. So we have 2850 grams of zinc. And then we need to convert that to moles. So we need the molar mass of zinc. And I have 65.41 grams of zinc. And that's in 1 mole. Now we have zinc, and so we ended up here with the zinc, and we can go from zinc oxide, and then we're going to go from this zinc oxide over to here. So we need to get to zinc oxide. So what's the mole ratio of zinc to zinc oxide? 1 to 1. So 1 mole of zinc for every 1 mole of zinc oxide that goes in there. Now, if you look at your second equation, or the first equation, we can go from zinc oxide to zinc sulfide. So the ratio of zinc oxide to zinc sulfide is 2 to 2. So 2 moles of zinc sulfide, and we have 2 moles of zinc oxide. And now we can take our zinc sulfide and get to moles of zinc sulfide to get to the amount of zinc sulfide that was originally there. So for every 1 mole of zinc sulfide, we go to the periodic table and we get the mass, molar mass of zinc sulfide. And I got 97.47 grams. And now we solve. So get me my answer. To 3 sig figs. I want grams.
4,250.
4,250 grams of zinc sulfide is what was in that ore. And it wants to know what's the percentage of that. So I'm going to divide that answer by the mass of that ore, which was 10,000 grams. And multiply that by 100, and that should give me 42.5% zinc sulfide. Okay, so we did a lot of dimensional analysis. There's a lot of steps in there. And we use 2 different equations, but we just take that one equation that bridges us, or that one compound that bridges us from one to another. Any questions on that?
Oh, wait.
Yes.
If it wasn't 10,000 grams of the ore, would you save your sig figs until after you had divided it?
Yes, you could have saved it to the end, because we still had 3 sig figs in the 10 kilograms.
Mm-hmm.
So I just went up there, and that's where I got my sig figs. Everybody good with that? Okay. The next thing I want to look at is limiting reactant. I teach limiting reactant way differently than the way you were taught in pre-AP. And I teach it a lot easier. So the first thing we need to do when we see so we read the equation. It says determine the moles of CO2 and H2O formed when 2 moles of ethane are reacted with 10 moles of oxygen. So we know we have 2 moles of ethane and we have 10 moles of oxygen. And I need to figure out how many moles of carbon dioxide and how many moles of water can be formed. So my first step I'm going to do is, we're going to find the number of moles. Oh, not mind, but find. Find moles. We're already in moles, so we don't have to do that step. So what we can do next is, so we're just going to list this. We have 2 moles of C2H6, and we have 10 moles of oxygen. And we want to find out who limits this reaction before we can do anything else.
So would you divide by the moles in the equation?
Yes, so our second step is to divide by the coefficient in the balanced equation. So in C2H6 we have 2, and in oxygen we have 7. So when we divide that, we get 1 and we get 1.4. So who is the limiting reactant? Who's going to run out first? Ethane. So this is my limiting reactant. Okay, so this doesn't matter to us anymore. This is an excess. So what we're going to do is we're going to go back to what we're given and find and solve for moles of carbon dioxide and moles of water. So we have 2.00 moles of C2H6, and we're going to use the mole ratio, and the ratio is 4 moles of carbon dioxide for every 2 moles of C2H6, and I get 4 moles of CO2. Next, we have to do the same exact thing for C2H6. So we have 2.00 moles of C2H6. Oh, we have to solve for water, sorry. And we have 6 moles of water for every 2 moles of ethane. And we should get 6 moles of water. And those are our 2 answers. 4 moles of carbon dioxide and 6 moles of water. Are there any questions over that? Okay, let's do it this time with grams. So here is our reaction, and we have 50 grams. It wants to know, calculate the mass of calcium nitride formed when 50 grams of calcium react with 50 grams of nitrogen. So the first thing we need to do is we need to find the number of moles. So if we have calcium, let me get different, and we have, say, 50 grams of calcium, and we have 50 grams of nitrogen. They're in grams, and we need to find moles. So calcium is going to get divided by the molar mass, which is 40.08. And I end up getting 1.25 moles. Nitrogen, its molar mass is 28.02. And I get 1.78 moles. So our first step says find the moles. That's what we've done. Next, divide by the coefficient. The coefficient in front of calcium is 3. And that gives me 0.417. The coefficient in front of nitrogen is 1. And that gives me 1.78. So who's the limiting? So calcium is the limiting reactant. So nitrogen means nothing to us anymore. So now what we can do is we can take our 50 grams and we can stoich that over to calcium nitride. But we've already done this math for the 50 grams. So we're going to start right here. Okay, so we have 1.25 moles of calcium. And to go from moles of calcium to moles of calcium nitride, we need the mole ratio. So there are 3 moles of calcium for every 1 mole of calcium nitride. And it wants to know the mass. So now we need the molar mass. Thank you. 148.26 grams for Ca3N2, and that is in 1 mole. So do the math. Gosh, having a hard time speaking today. And what do we get? To 3 sig figs. $61.8 grams of calcium nitride. Is everybody okay with that way of doing limiting reactants?
Yes.
It's what we're going to do every time we do limiting reactant.
What was the harder way that they did it?
Where you would take it from we would take 50 grams and stoich it to calcium nitride, and then we would take 50 grams of nitrogen and stoich it to calcium nitride, and then take the lesser of the answers.
We honestly never did that.
Why would they make us do the harder one?
It's just a way, I don't know. That's the way I used to do it until I started teaching AP, and
Realized that this was way easier.
it was way easier.
It's like half the work.
Half the work, yeah.
Just
Joe.
Maybe this is why Joe wasn't confident in his ability to see.
We're recording, Andrew. We're recording, sir. All right, let's try another one. This is some, we're going to put in some combustion in here. So we have 3 more problems to do. So here we have methanol, and it is manufactured by combining gaseous carbon monoxide. So we're going to take carbon monoxide, and we are going to combine that with hydrogen gas, and we're going to get CH3OH. Suppose you have 68.5 kilograms of carbon monoxide, so we're going to change that to 68,500 grams. And it's reacted with 8.6 kilograms of hydrogen gas. And we're going to turn that to 8,600 grams. Calculate the theoretical yield of methanol. Okay, so what is theoretical yield? Anybody remember what theoretical yield, how to calculate theoretical yield? Huh?
All your reactants.
No.
Is your actual yield over your
Actual over theoretical times 100. Okay? So actual is what we get in the lab. Theoretical is in a perfect world, what would we come up with? And we get that number by doing the stoichiometry. Yes? We are going to balance it. So here is my actual right here. So we got a lot of information up here, and we are going to, first thing is balance it. So what is the number, how do we balance that? Two in front of the H2, and that should, we're good. So we want to know how many grams of CH3OH we can theoretically make. So first of all, we need to find our limiting reactant. So we're in grams, so the first thing we need to do is go to moles. So we're going to divide carbon monoxide by 28.01, which is the mass. And to 3 sig figs, I've got 2450 moles. For the next one, I divided it by 2.016, and I got 4260 moles. Everybody good with that so far? Our next step is to divide by the coefficients. So the coefficients in front of CO is 1, coefficient in front of H2 is 2. So 2450, and for hydrogen I got 2130. So who's limiting? Hydrogen is the limiting reactant, which means carbon dioxide means nothing to us now. Carbon monoxide. So again, we're going to start at our moles. So 4250 moles, 60, thank you. Moles of H2, and the ratio of H2 to methanol is 1 mole of methanol to 2 moles of H2, and then we need the molar mass of methanol. Did y'all get 32.042? Grams per 1 mole. So to 3 sig figs, I got 68,300 grams of H2. So theoretically, we can get 68,300 grams of H2. Not H2, C3OH. Sorry, CH3OH. But in all actuality, so actual over theoretical, we actually got 3.57 times 10 to the 4th grams. Theoretically, we could get 6.83 times 10 to the 4th grams times 100. To 3 sig figs, what do y'all get? 52.3? 3% yield. Okay, so it's a lot of steps. Go back and see what you're doing. You will have something like this on your test where you have to find the limiting. Once you find the limiting, you have to go and find your actual or your theoretical. And then once you find your theoretical, find your percent yield. It's a three-parter. Yes?
Oh, wait, where'd you get the 357 times 10 to the 4th?
That was up there at the very last sentence.
Okay, I see it. Sorry.
Any other questions? Yes?
When you rounded the 2450
Uh-huh.
on the carbon monoxide
Uh-huh.
because of sig figs, but then you had 3 sig figs for your hydrogen. You had, because it was 8,600.
Oh, yeah. Actually, yeah, and I was just rounding along the way. At the very end is where your sig figs is really going to matter.
Well, yeah, but with that, I mean, I'm pretty sure that probably would have changed. But that made the answer wrong.
It wouldn't have made, I mean, if your answer would have came up to be 53.4% or something, you're still within like 1% of my answer. So,
Okay.
so all based on rounding. If I'm looking at your rounding and your rounding is different, then your answer, if you're not exactly the same answer as me, then you're okay.
Okay.
You just have to be within a certain percentage. All right, so that is one thing. Y'all want to know what's the test? I'm telling you right now, you'll have a question like this where you'll have to do 3 parts to it. And so let's go to 36. And this is something like you would see on your exam. A common laboratory method for determination of arsenic is described in the reaction. If 2.50 grams, so we have 2.50 grams of AS2O3 and 4.50 grams of I2 and 4.00 grams of H2O are mixed, the reaction proceeds to completion. Which reagent is the limiting reactant? So the first thing we need to do is find who's limiting. So we have 2.50 grams of AS2O3. We have 4.50 grams of I2. And we have 4.00 grams of H2O. So we are in grams. Our first step is to find moles. So divide everybody by their molar mass. So I'm going to put these numbers there. Somebody get the answer for me. So for the molar mass of AS2O3, it is 197.84. I2 is 253.8, and water is 18.02. So what y'all get for AS2O3? 0.0126. What do we get for I2? 0.0177. And for H2O? 0.222. All right, those are moles, right? So we need to divide everybody by their coefficient. So AS2O3's coefficient is 1, which is going to give me 0.0126. Iodine's coefficient is 2. And water's coefficient is 2, which should give me 0.111. So we need iodines. 0.00885. So who is the limiting reactant? Iodine. So our first answer is the limiting reactant is I2. So answer 1. Next, calculate the mass of arsenic, which is theoretically possible. So we know iodine is where we're starting. We've already done part of the math. We can start right here with the moles. So 0.0177 moles of iodine And the ratio of iodine to arsenic is, for every 2 moles of iodine, it is 1 mole of As2O5. And then we need the molar mass of arsenic, which we just take the molar mass of As2O3 and add 32 to it. Where did I get that? Because one has 5 oxygens and one has 3, so I just added 2 more oxygens to that mass up there. So the 197.84, add 32 to it, and I get 229.84. And what do we get for our theoretical yield?
Uh, 2.034.
2.034, so 2.03 is our theoretical yield. So theoretically, that's what we should get. Now, actually, we went into the lab and we only got 180 grams and it wants to know what's our percent yield. So actual over theoretical times 100. Our actual is 1.80. Theoretically, we should get 2.03. And what do you get to 3 sig figs? 88.7% yield.
What's the highest percent yield you've ever gotten on the lab?
That I've ever gotten? I've gotten like 97% before.
Well, last year,
I don't know if you remember, but Joe, we did percent yield for one of the labs, and I thought I got like a 97%.
Yeah.
Yeah.
I always tell my students if you get less than 90%, then you're probably going to get fired if you have a job. You can get over 100%. How can you get over 100%? Your lab technique, something's wrong with your lab techniques. You're bad drying, you have impurities in there, you've contaminated it. I mean, so sometimes you will get over 100%, but it's from mistakes.
last year I think we got 98%.
No,
And
I got 98.
No, you thought you got 98%.
You got 80 something percent.
Make sure
We
I
started
do something.
with 80, but then we
Oh, y'all
remember because we had it wrong.
Okay, last problem. This is a problem that I would know how to do. Hint, hint, hint. Star it, asterisk, star the one before. You want to know what's on the test. This is something you're going to see very similar on the test. You probably saw something similar to it on your homework as you're working it. All right, a 0.00300 gram sample of naphthalene, a compound containing only carbon and hydrogen, was burned in excess of oxygen so to give 0.013 grams of carbon dioxide. Determine the empirical formula of naphthalene. The formula weight is 128 U, and determine the molecular formula. So we got a lot of parts going on here. So the very first thing is we know this compound is a hydrocarbon. It contains carbon and it contains hydrogen. I do not know in what ratio it contains hydrogen and carbon. So my subscripts are X and Y. It is burned in excess with oxygen. And we know when a hydrocarbon is burned with oxygen, it produces what two things? Carbon dioxide and water. I cannot balance this equation because I do not know what X and Y is. Okay? So let's go to the next step. a 0.0030 gram sample of naphthalene. I don't know what the formula for naphthalene is, but I know that we have 0.00300 grams of it. It's burned in excess of oxygen, so oxygen is not part of this right now. When it is burned in oxygen, it gives how much carbon dioxide? 0.0103 grams of carbon dioxide. All right, looking at this, we know carbon is coming from, in carbon dioxide, carbon is coming from one place, and what is that? It's coming from the hydrocarbon, the naphthalene, right? So we know that the grams of carbon in our product here, the 0.0130 grams, is going to equal the amount of carbon that went in it, the CH hydrocarbon, right? What goes in must come out. So if we get 0.013 grams of carbon dioxide, whatever of that is carbon has to have come from naphthalene. So, because we know this, we can figure out how much carbon was in naphthalene. So let's do some stoichiometry here. So we have 0.0103 grams of carbon dioxide. And I want to get this to moles. So in every 1 mole of carbon dioxide, there is 44.01 grams of carbon dioxide. Everybody with me? Okay. If I have 1 mole of carbon dioxide, how many moles of carbon are there? I need to get to grams of carbon. How am I going to get to grams of carbon? If I have 1 mole of carbon dioxide, how many moles of carbon do I have? 1. So, in 1 mole of carbon dioxide, there is 1 mole of carbon. And I need to get to grams of carbon because I want to know how many of that 0.0300 grams, how much of that was carbon. So we need the molar mass of carbon. So in 1 mole of carbon, there is 12.01 grams. So do that math for me. Tell me, how many grams of carbon? 0.00281. 0.00281 grams of carbon. But my hydrocarbon weighs 0.00300 grams. So if I know how much carbon I have, how am I going to find out how much hydrogen I have? I'm going to subtract. So 0.00300 grams minus my carbon, 281. And that tells me that I have 0.00019. Is that right?
My calculator put 1.9 e to the negative 4.
1.9 e to the negative 1, 2, 3, 4. That would be right? Okay. Grams of hydrogen. All right, I know how many grams of hydrogen I have. I know how many grams of carbon I have. So how can I find this formula, empirical formula? All right, so carbon, 0.00281 is going to get divided by the molar mass of carbon. And hydrogen, 0.00199, is going to get divided by the mass of hydrogen. So now I get 2.34 times 10 to the minus 4. What do we get for hydrogen? So 1.97 times 10 to the minus 4. So our next step is to divide everybody by the smallest. So everybody gets divided by 1.97.
Everything gets divided by 0.00234.
234 smaller.
Yes, 234. Yeah. Oh, maybe I put a bunch of zero in there. Sorry.
And then I get a 1.2 and 1. Is that right? So my formula is C 1.2 and H 1, but we can't have that. So we need to multiply everybody by 5. And what do we get? C6H5. I hope that works out because mine says I multiply everything by 4. Okay, so this is 1 point, so for the hydrogen it's 0.0019 grams. We're going to take away this 9 and we end up with 1.87 times 10 to the minus 4. 8. Okay. But still, when we divide by the smallest, we get 1.25 for carbon, right? Around there. 2.34 divided by 1.88. So, yeah, about 1.25. So, if I have C 1.25 and H 1, we need to multiply each one by 4 to get C 5H4, and that is our empirical formula. So because I went one step too far, or one place too far on the carbon, it kind of messed my answer up.
But I mean, that could get your entire question wrong, right?
It could get your entire question wrong. But if I go back and I see your math and your math is sound, even though you didn't get the right answer, but your chemistry is sound, then you would get your point. You just, because you went too far, one number too far. But everything else is right. It's just you went off that math to get to your answer. And you would get your point. So that is our empirical formula. The molar mass of the empirical formula is 64.09. And I'm running out of room, so I'm going to go back up to the top. So if my molecular formula is 128, and my empirical formula is 64.09. When I divide them, I get 2. So the formula, molecular formula for naphthalene is C10H8. Okay, so when you're doing your homework, again, work this problem. If you have questions, then text me and let me know. But this is a problem that you better know come Thursday.
Can we text you through the remind?
You can text me through Remind, yeah.
My brain feels dead.
This Z? Or
I think it was
Brain
one,
feels dead.
maybe it was F that had a problem like this on it.
Oh. And
You
then
would know
I
if
had
you did it,
math
maybe.
next time and no shit to do anymore math.
it's all a blur.
Okay, so that is it. I am done.